Hello, thank you all for attending. Um, it'll be fun to adjust to this virtual conference experience. Can everyone see my screen? I should be sharing my presentation now. So I'll be talking about Baremetal RISC-V Renode. So first I'll give an overview about what each of those terms mean, and then I will go through some code examples on how to set up kind of a basic environment and how you can run some of these examples yourself. Okay. Can you see the slides now? Oh, okay. Good thing I double checked. All right. So I'm Zak Kohler. Originally, I went to school for chemical engineering. I've been programming a lot longer than before I went to college. And my day job used to be a materials engineer, and I've really turned into a software developer. Some of my interests that are relevant to this talk are programming, electronics, and retrocomputing. And some of my not so relevant interests include drawing, punk rock, and making cheese. So what is my motivation for this talk? So computer systems are built off of layers and layers of abstractions. And these simple interfaces allow complex systems. So every time you send a text message, you don't think about the radios involved. You don't think about the kernel on your phone. All of this is considered good because it allows you to do something very complex using something simple. When you're looking at doing anything with a user application in a computer system, you're interacting with this very top layer, the application, and that'll talk to an operating system. At the layers of the levels below that are kind of invisible to most software developers, and everything below the application is kind of transparent to the end user. So kind of what motivated me was I didn't understand how kind of CPUs worked and how what an instruction set really was. I kind of knew how assembly worked, but I wanted to learn more about hardware. And so over the last couple of years, I've been building some simple hardware projects where I breadboarded a motherboard and connected a CPU to one chip of RAM and kind of single step that hardware CPU. That was a Z80. And I just built kind of a toy clock and ran it at about 1 hertz. So every time I pressed the button, it was 1 clock cycle. And then after that, I kind of moved on. I said, okay, that's a CPU, that's a microcomputer that was used in early PCs. What if I built my own CPU and I could kind of look inside of that CPU as it was going? So I built this simple CPU in Python where you kind of could connect memory, you can connect the CPU, and you can code your own instructions. I actually built a assembler for that CPU. And so this talk is kind of my next step on this journey of understanding the interface between hardware and software. So Baremetal RISC-V Renode. As I said, this is my next step, and it's kind of a vendor-free environment to write and play with these toy operating systems. So operating systems sit right between the application and the hardware. Before I was kind of messing around with the CPU architecture, and now I've moved up just a little bit. I'm kind of like playing in this area. What sits between applications and the hardware? So you have drivers and you have an operating system, and fundamentally, the Linux, it's a kernel. It's the operating system. It talks to the hardware. So what does bare metal mean? Bare metal is if you compile a C program into an executable, normally if you just run GCC and then all of your C files and header files, you compile it into a binary and executable, but it still relies on the operating system to host that executing process. it allocates the stack and memory for you, and it takes care of some. Anytime you need to interact with hardware, you can make a API call or a system call to the kernel. So you don't have to write something to access a disk. You don't have to write something to access a file. When you compile Baremetal or with GCC, it's dash freestanding. You're telling that compiler that you're going to run this C program, and there's not going to be any operating system that you rely on at all. So why would you do that? Well, if you're writing an operating system, you're not going to rely on another operating system. So when you compile a Linux kernel, you'll do dash freestanding, and that says, there's no main, there's no entry point. That has to come from somewhere else, like a bootloader. You're just writing a binary blob that has CPU instructions. Also, if you need to write something like a driver and you need to access the hardware directly, or you're doing an embedded system where you don't want to rely on an entire operating system, you can also compile this way and have your own bootloader. So this gives up everything that Linux gives you, but when you do that, you can use it to learn a lot more about why you really should love Linux. Sometimes when you need something lighter weight, you don't want a full Linux kernel to be shipped on a Internet of Things device. There are also minimal, very small operating systems that are kind of taking that role of sitting between you and the hardware, and those are called real-time operating systems. And they have a different performance trade-offs than a kind of full desktop Linux. But we'll talk about that a little more. So what is RISC-V? When you read it, it says RISC-V, but it's actually pronounced RISC-V. It's the 5th iteration of an open standard instruction set architecture. So basically, if you think like Intel CPUs and AMD CPUs are x86, and then mobile devices are almost all ARM, and then you have all these different ways that you can compile an executable and tell a CPU how to compute certain functions. RISC-V is kind of the 5th generation of this open standard that they've made, and it's finally been tuned. It was more of an academic thing until it got to this 5th iteration where they realized we've learned a lot over the years from things like Spark and MIPS and Alpha, and we're going to take the best of all of these closed source worlds and put these concepts into an open architecture that can scale from embedded all the way up to supercomputers. So it's kind of poised to be the next big architecture. I just saw they released a dev board for a PC in RISC-V a couple of days ago. So it's kind of a very nice orthogonal instruction set to learn on, and it's probably going to be the future. So what is Renode? It's a simulator designed for testing and debugging embedded firmware. So you have QEMU, but that's kind of you classically use for running desktop applications across architectures on Linux. But Renode is a little bit more friendly to embedded devices. I found it has a really nice tool set. You can add LEDs to blink. You can add serial controls, and it's all configured by a very simple configuration file format. And you could even set up networks of multiple devices and simulate that all as a whole. And you can also like piecemeal out, simulate some, and connect real hardware to some. So it's kind of like a hybrid simulation environment. But it's growing in popularity among a couple different sets of people. Embedded and like FPGA embedded also you can run using Renode. You could think of a emulator when you're playing a video game. It has one single processor and a certain graphics card and a certain way to produce audio. And all of those are tuned. Like if you have a Nintendo, it acts a certain way and it's always configured the same way. Or some other platform would be kind of like a static. Renode, with the configuration file, you can say add the different pieces of the CPU to whatever you want into that system, and then put it in and load your ROM onto that system. So what is my tool chain? I use the GCC RISC-V tool set. So in order to run RISC-V, we're going to need to make a cross-compiling toolchain. So you can't use the GCC that comes with your system. You have to build a special GCC that will run on x86 but compile to RISC-V. So once you build the toolchain, it takes a while. You can pull down the sources and compile from scratch. And the thing that you'll be running will be of many others, it's calls, but it will look like this, RISC-V 32. So that's the architecture. It also comes with the GDB, bin utils, and other executables in that toolchain. So Renode, it runs on the Mono framework, so it's actually a .NET app, but it also has some native components. You can also compile this from scratch, and basically, once you get it compiled, you just feed it this hardware configuration, and you could set up a custom hardware platform for whatever you're simulating. So if you have a certain development board, you could tell it how much RAM, tell it what kind of CPU, and plug in different levels of emulation for each of those components. And it does like the logging and input output for that. So the first thing we're going to go over is a simple example. We're going to blink an LED. This is the fun part of the talk. So basically, if you pull down my repo, this is the bare minimum you need to get started, is if you get into the _blinky folder, activate the toolchain and call make launch. You start up the Renode emulator, and this is the monitor terminal that controls Renode itself. And you can see I've turned on logging, and this is the LED blinking. I don't have a physical LED, but I'm logging out whenever the LED turns on and off. And the really cool thing about running this in Renode as compared to, say, putting it onto actual hardware, is it's very easy to recompile and change and make it do something different. And it's also very easy to debug. So I've also set up the debug commands so that it has started a GDB server here, and I can go in and see exactly where in the assembly and in the actual compiled binary we're stepping. And so now at this GDB prompt, if I wanted to step through the instructions one by one, you could see we're in the delay loop. It's a very big delay loop when you're going at 1 Hertz. So what we're going to do is set a breakpoint, and at the toggle LED location. Let's see if I got this right. Okay, so now I've set up a breakpoint here, and now I can continue. And now it's running through the delay loop. It's slower because I have GDB attached, but finally we get here and we break, and we're going to step through these 4 instructions. We're going to read in the old LED state into a register from RAM. We're going to XOR with this bit mask here. So this is LED 1 and this is LED 0. So we're only going to be toggling LED 0, and you can see where it says LED state changed false, state changed true. And we go through here. I will say step instruction. So now we've read the state, we've applied the mask, we swapped it out, and then we write it. So we got the state change, and now it says false. Now we go through and we're back, we're stuck, we're in that loop again. So if I say continue, I get back in there, and we could do that again. So I'm going to quit here, and it ends the Renode session, and now I can exit from GDB. And if I wanted to change that bit mask, come in here, and you can see where we've said how much to delay, but here's the mask. So I'm gonna just change this to a 1. So now it's masking both LEDs. And come over here, I can recompile. So it ran this RISC-V GCC Baremetal, and now you can see both LED 0 and LED 1 are both blinking alternately. And so as you can see, it's a very fast iteration environment where we can go through and change your software, change the firmware, reload it into hardware and test. So if you're building something substantial, this is great. You don't have to wait, make some image, flashed onto a chip, and then get some feedback. And then how do you debug? And typically you'd hook up an actual hardware debugger or some sort of JTAG so that you can get GDB on the real hardware. But for the first 95% of integration, it would be really nice if you could do it all on your laptop, especially if you have a fast emulator. So what did I just run there? When I say there's a configuration file for Renode, this is what I'm talking about. This entire thing specifies the platform, the system. So I say we have memory attached to the system bus at location 0, and the memory is, this is hex, but it's a certain number of bytes. It's way more than I need. And we specify that we connect a CPU also to the system bus. So basically, it's like kind of like plugging. You could think of system bus as plugging into the motherboard. And then the only thing that's in the motherboard are these 2 LEDs and a piece of GPIO hardware. And you can see where it says at system bus with a certain memory location. What that's saying is it's memory mapping your GPIO port onto the memory at a different location. So if you were to write an assembly to read and write to memory, or to one of these locations below 40,000 hex, you'd be manipulating an actual stateful memory. But if you interact and use your CPU instructions to read and write to this location, you're writing to the emulated hardware and putting the state of what you want the LEDs to be into this location. So what we were doing in that assembly level program that we just looked at, we were reading and writing a byte to this memory location, and that byte was being then taken by the simulated hardware and put out onto the LEDs. This is showing how to make a connection. The arrow means connect this GPIO port 0 up to this LED that's defined here. So here we say we have LEDs, and here's where we say make the connection from GPIO to the LED. And then we turn on debugging for that LED. And so that sets up the hardware platform. Initializing the hardware platform, so actually loading in our firmware and doing everything it takes to run, is this simple. Basically, we create a machine. This is kind of like boilerplate, load platform description, and this Vex RISC-V Renode platform, that's this file. So basically, it's a script that's saying, we're going to create a new machine and we're going to load this platform. And so we have one instance, we have one machine. We're not creating a network here, but we could. This is a single machine. And then we load into that machine an ELF image. So it's actually the same exact file format. We don't use a custom Baremetal format or raw binary. We use an ELF format. And Renode knows how to load that and put that into memory for us. So it knows where the memory starts, and we are able to load our image directly into memory. And then the CPU has a certain location where it knows to start executing from. So it's not main, but it's a actual memory location, I think 0, or maybe it's a different jump address. This starts a GDB server. So this is like plugging in your JTAG, and this is turning on logging, so we can actually see the LED blink, and then start is just start. Any of these commands could be typed into that little black Renode prompt that you saw come up, the monitor. But this lets me do it repeatedly every time when I do a launch. And the program we already kind of peeked at. So now that you understand kind of what the hardware register looks like, here we're defining a constant of what that memory location is. And we're saying read from that memory location. We put that in here. I just leave that in register A5. That's not how it would really be done, but that's how I do it in this small example. Stored into register 5, and we read the values from it, apply that bit mask, and then rewrite it to that memory location. And then the simulated hardware or emulated hardware will pick up that change when we write and toggle that LED. So everything that it takes to make this ELF binary is right here. So right now we only have an assembly file, but you can also compile C to Baremetal. That's very easy, as standard. I turned on GDB so we can have all the symbols in reference, so that when you're in your GDB console, you can reference particular spots in memory. Turn off optimization so that your instructions can map directly to lines of code rather than jump around or inline some functions. This gives you kind of verbatim what you've asked for. Name of your output file, and we tell it don't use main, don't assume we have an operating system, don't rely on any header files having the same semantic meaning, and don't use a standard library. So it's basically mechanically translating C code into machine code in RISC-V. So now we're going to make a serial port or a serial connection, and we're going to write a driver for it. In Linux, you kind of have an interface that you would implement maybe a character or block level driver for a device. Here, we're going to talk just directly to the hardware. So there's no abstraction for writing a driver. It's not a module that we can load or unload at runtime. It's just we are talking to the hardware register just like we did with the LED. So this is a more complicated example. I'm showing the code at the same time. Let me move this preview. So first, I'll talk about the assembly. What do we need to do to get a serial driver running? Here is the memory location that we're going to be accessing. So this UART base, UART is universal asynchronous. I'm not sure, but it's a serial connection, or it can be put over serial. And each of these are the offsets for receive and transmit, and then different signals. So if the buffer gets full, or if there's nothing to read, these signals are turned on. And writing ones and zeros to each of these registers, which are offset in memory from this base, allow it to read and write to that piece of hardware. So it's memory mapped I/O, and it's going to be a serial port. Other things that we didn't have to do when we were just doing a blinking LED, one of them is set up interrupts. So all of this code from line 17 down to 42 is turning on interrupts, saying where to jump in the binary when you do hit a machine level interrupt, so the handler for that interrupt, and setting up a stack so that we can use C functions. And when you do a context switch, it'll take all your registers from your CPU, put it into the stack, and store it for later. So when you return, you can put those back. For a while, I didn't set up the stack, and when I'd call a C function, it would just keep overwriting the same spot because there's no stack pointer. And so basically, there was no stack, and I couldn't return out of the function, so it would just go execute off into nowhere. It was kind of mysterious behavior, but that's what you don't get any of those luxuries. You have to set that up yourself. Everything we're running here is at like the machine level or M mode, so it's not supervised mode. This is like running in like the ring 0 or ring 1 of the in like the highest privilege ring in x86. That's what machine mode is. We don't do anything with making other processes. We're running kind of as a kernel here. And all the driver is this. MTVec is whenever we get a machine level interrupt, right now we're just going to assume that it's the UART because it's the only piece of hardware that's attached. It's the only thing that could throw the interrupt. And so what we're going to do is receive that character, and we're going to call this function. This is a pseudo instruction that will call this, which is defined in C. And fancy character basically says we have this character array, and we're going to plug in a single character. So kind of surrounding a character by a bunch of hash signs. And we had to write the print function, loop over those characters, print them out, and make sure we get the right UART base in there into the register that we're going to use, because you can see we're putting the UART base into register A2, and then this putc that relies on that A2 being your UART base, and we're saying write this character, this byte, into the register RXTX, and then it fires off with the hardware, and the hardware knows how to connect that to my GUI. So let's run through this or do a demo. So hit make launch, and we're going to get the monitor window here again. And over here, I'm going to connect via telnet to a telnet server that Renode has spawned for me that connects up to that virtual UART. So the UART has an interface to say, hey, connect this to a virtual serial. And so now when I type into here, it receives the character and echoes it back to me. Hello, OLF. And it just prints it back, echoes it back, but fancy. So all of this is just to handle that interrupt and get back to you. So that's that example. Let me close out here. Okay, so let's bring it all back together. So kind of the theme here and motivation is understanding how operating systems work. Kind of take it for granted that you plug in a hard drive and you can partition it and just start writing files. But there's so much more. And the reason that operating systems even exist. So I always like to say the first operating system were human operators. It was literally a system that they followed. Everything was batch processed, and you had kind of one set of instructions that you would run on a new set of data over and over again. And every single program had full control of the system, like I just did. Any instruction could write to any bit of memory, and it would just run through straight, and there were no interruptions. Things changed when you finally had like a PDP-1. It's an interactive system where you could say interrupt the program and have something else happen. And so what an operating system gives you is a way to get away from the hardware. They give you standard interfaces to talk to the real world. These come in the form of drivers, memory allocation, file systems, and processes. So the example I just showed you didn't have any processes. So that's kind of the next step that I want to take. I want to start building a real-time operating system that you would be able to take a small another program and load it at runtime. Like I could type into my serial terminal a command and load in a new program that runs and interacts with that virtual operating system, or the small RTOS. The other thing that operating systems do is instead of doing one thing all the time, so right there I was sitting in a polling loop saying there's nothing to do, I'm waiting for an interrupt. Back in the batch processing days, you wouldn't do that. You'd sit there and run all the way through. When you time share and you have a whole bunch of processes, you could have two programmings running at once, and it's kind of like chopping up the time of your program, saying, okay, run this for a millisecond, run this other program for a millisecond. You have 200 programs running at once. And so it's kind of interesting to think, like, if you had to change your card deck 100 times a second, it'd just be impossible. So other things that I would explore in this kind of area is how to do process control. What would it take to make a simple program that could run on the bare metal and display you up a little menu and allow you to run another ELF. It could be the loader for the next ELF program. So what is the minimum amount of code where you can make a loader for another program? It shouldn't be too much. Concurrency. So instead of just loading one other program, how could I make it split the time of the CPU between running more than one other program at a time and share the hardware? That's a much harder problem, but it'd be very interesting to understand that. So one method is kind of a simple polling loop, but you could also do something more fancy. Memory management. So how do you say this program you get this little piece of virtual memory, and this other program you get another piece of memory? Basically, you work with the hardware and tell the hardware this is running under this context, and you only get like this small amount of memory. And it looks like it has control of an entire world, but really it's just kind of a subset. How do we handle it when we do like a divide by zero, a software interrupt? Something bad that happens in the CPU, you need to recover from that. So all of these things could be explored by developing an RTOS, or a real-time operating system. Just something very minimal, a toy operating system, just something for learning. There's production RTOSs like Zephyr, but I just want to build something to learn. And after that, I'd love to run it on Renode and then run it on real hardware. There's a whole bunch of people that they build. They have hardware development boards for their hardware, and then they build the Renode models for you, so you can pull in their platform, test. You could test and develop software and not even have their hardware. So I want to know what that process is like. So thank you. I'm not sure on my time here, but I want to cover basically what I've covered here is available on my blog, or will be soon, and I'm going to be covering building kind of a real-time operating system and following some more of these follow-ups just to learn more. There's a very good YouTube series. If you search Miros or Miros Samick, you'll find it's like a 17-part series on building a real-time operating system after he teaches you the fundamentals. And he doesn't use Renode and he doesn't use RISC-V. He's using ARM and he's using real hardware. But it's a really good introduction to modern embedded development. So I'm going to kind of make a RTOS in the spirit of his RTOS, but with RISC-V and using Renode. And if you want to follow that, I'll be announcing those on my Twitter handle, Y2KBugger. Thank you.
Well, thanks everyone for being part of Zak's presentation here. We do have some time for questions and answers, so we'll pause here briefly. If you have a question for Zak, please put it in the Q&A section of your Zoom session right now. And just a reminder for those of us who are joining on the internet at large via our YouTube stream, if you would like to participate in the OLF conference experience,